Good afternoon, Southminster Scholars. Welcome. Today we're going to talk about the formation of our solar system. The formation of our solar system is fairly straightforward. The collapse of a rotating gas cloud leads to planets to circular orbits around a star. That's pretty straightforward. Rocky planets gradually increase in size. Giant planets start with rocky and icy cores, then grow by accreting gases from a disk. The question then is, how did organization come to be? Astrophysics is concerned with both the contents of the universe and the physical processes that control their development. Let's watch today as Dr. Summers explains this in greater detail.
Because I'm a professional astronomer today, some folks assume that I always wanted to be an astronomer, that I grew up with telescopes and studying the sky as a hobby. Well, the truth is, I didn't think about being an astronomer when I was young. My favorite thing was, and still is, solving puzzles. I was always good at math, and I really enjoyed the word problems. In high school calculus, the best word problems came from physics. So I majored in physics at college. As I progressed in physics, the most interesting physics problems were in astronomy, and I did my graduate work in astronomy. So it was a sideways route, from mathematics to physics to astronomy, and always with an analytical bent. Those who grow up with telescopes tend to be what we call amateur astronomers. Now, I don't want to use the term amateur to imply a lack of expertise. It more implies that they don't get paid to do astronomy. These folks tend to focus more on observing techniques and the qualitative aspects of astronomy. To get your PhD in astronomy, you really have to delve deep into the mathematics behind the celestial objects. This is sort of a fundamental dichotomy between descriptive and quantitative astronomy. Astrophysics research is concerned both with what is out there and with how it came to be that way. Today's lecture explores the latter half, the formation of the solar system. The basic idea is called the nebular hypothesis, and it's originally due not to an astronomer, but the philosopher Immanuel Kant. In 1755, he came up with this idea. In this drawing, you can see it starts with an immense cloud of low-density gas. Gravity causes this cloud to collapse, and as it collapses, rotation naturally forms a disk. The planets form in circular orbits within this disk. Eventually, you end up with the solar system as it appears today. This is a nice descriptive story, and it sufficiently explains all of the qualitative aspects of our solar system. However, when you look in detail, you find that some parts are not yet fully explained. Let's begin on a much larger scale. Let's look at the scale of galaxies. This is a spiral galaxy, Messier 51, also called the Whirlpool Galaxy. And galaxies are composed of stars, gas, and dust. And this image, which was taken with visible light, the stars are the most prominent things you see. However, if you use the Spitzer Space Telescope and look in infrared light, the infrared light reveals the warm dust. This is the dust inside the spiral disk of this galaxy. And you can see how it's threaded throughout the galaxy. It's not just concentrated in the spiral arms, it's all over, threaded in throughout the galaxy. These spiral galaxies have these flat disks that are basically shaped like a pancake. And if you look at them edge on, here is a galaxy named NGC 5861. Looking at it edge on, you can see dark dust lanes. These dark dust lanes show the cold clouds in the galaxies, and these cold clouds are where stars form. Now, how big of a cloud would you need to form a star? You can make a simple estimate by taking the mass of the sun and divide it by the average density of the interstellar material. Doing that calculation, you find that you need about 1 light year cubed as the minimum size cloud necessary. So take 1 light year, 1 cubic light year of interstellar material, that will collapse down to about 1 solar mass. But generally, you're not going to have a full efficiency. Not all of that mass is going to go into the star, so you need about 10 times the mass of the star in a protostellar nebula. This image here is an image of an object called a Bok globule. It's the big dark splotch in the middle of the image. It's dark not because there are no stars there, but because it's a dense, dark cloud that's blocking out all the light of the stars behind it. It's roughly 1 light year in size. And this is really not a full interstellar cloud. It's just a small core of interstellar cloud within much, much larger interstellar clouds that we call giant molecular cloud. These giant molecular clouds can contain as much as 1 million solar masses. And so they're much, much bigger than these few solar mass Bok globules. But still, even these giant molecular clouds are small compared to the trillion solar masses. That's the total mass within a galaxy like our own. To form a star, such a cloud undergoes gravitational collapse. And gravity is a rich gets richer scenario. If you have just a little more mass here, you also have a little more gravity. And that attracts more mass. Having that more mass provides more gravity, which attracts more mass, which gives you more gravity, and so on. Regions that are overdense, that have a little bit more mass, tend to grow and grow and grow. This collapse, however, can be slowed or stopped by thermal pressure. Now, thermal pressure is the idea that gas collides and heats up. And when you heat something up, an increase in temperature also creates an increase in pressure. We call this thermal pressure, and this thermal pressure can provide a force that pushes out that resists the collapse force of gravity. So in order to remove this thermal pressure, you need to be able to radiate away this heat, radiate away that heat energy, remove the thermal pressure, and the collapse can continue. Here are some interstellar clouds seen using both infrared light and radio light. The warm clouds are seen in infrared, and they're shown here in green. The cold clouds are seen in radio light, and they're shown here in red. Now, if you look at a couple of these clouds closely, you can see that the cold regions, the red regions, are shielded inside of green regions, the warm regions. These dark clouds, the dark cold clouds, are inside the warmer clouds. And stars form in these dark clouds because that is where the gas can cool. They're shielded, they're inside. This is where you can cool, and energy can be radiated away. If you want to put it another way, if you see a bright cloud, that cloud has been heated up, and those are hot clouds, and that's not where you're going to get a star forming. Now, once the cloud starts collapsing, the question is, will it have enough rotation to form a disk? The concept involved here is one called angular momentum. And before we get to angular momentum, let's first discuss normal momentum. Momentum is defined as being mass times velocity. And to understand it, I tend to think of car crashes. If you take a Hummer, big old heavy Hummer, and a small little Volkswagen, and you crash them together, which one's going to win? Well, the Hummer does, because it's more massive. So mass is important. But what if you take a Hummer moving at, say, 10 miles an hour, and another Hummer moving at 70 miles an hour? In a crash like that, the high-speed Hummer is going to win, and that shows you that velocity is also important. So mass and velocity are both important when considering motion. Momentum is the combination of mass times velocity, and this is a conserved quantity in elastic collisions. I will, of course, note that car crashes are definitely not elastic collisions. Angular momentum is simply momentum, but for a circular motion. It's mass times velocity, also times the distance to a pivot point. You can think of this as sort of spinning or orbiting momentum. And angular momentum is also conserved in a system. So we can check the spin of a collapsing nebula and see how much rotation it would have when it gets small. It starts out at about 1 light year, right? And when it finishes, it will be down around 100 AU. Now, 1 light year is about 65,000 AU. So just to make things approximate, let's say the radius goes down by about a factor of 1,000. That means, since angular momentum is conserved, that the velocity will go up by a factor of 1,000. The period depends on both radius and velocity, and the period will go down by a factor of 1 million. So if the cloud is initially rotating very, very slowly, say that this 1 light year cloud is rotating once every million years, by the time it gets down to the size of a solar system, it will be rotating once per year. That's plenty of spin to form a disk. The next stage, once you've formed a disk, is to form the star at the center. How do you form the sun? And here's where the spin actually becomes a problem, because there's really too much spin. The star is, again, much, much smaller than the disk we just talked about, and if you continue that collapse scenario, then rotational support will prevent collapse. The centripetal force will push out and stop that disk from collapsing down to form a star. So in order to form a star, you actually need dual formation paths. Starting with this giant cloud, only the inner parts can really collapse down and form a core of a star. Not a full star, but the core of the star. The outer parts will collapse down and form a disk, and somehow you've got to get that material in the disk to feed onto the protostar. Now, the way this is done is kind of complicated. The interactions in a disk, can be quite difficult to analyze with mathematics. But there is one simple overall principle. Mass flows inward and angular momentum flows outward. That was about a month of graduate school going through the equations, figuring out that that really is true. Okay? So I've just saved you a month of graduate school there. Mass flows inward and angular momentum flows outward. So some material feeds onto the protostar as the mass flows inward, and some material is then flung outward to large radius to take the angular momentum outward. We call this stage the T-Tauri stage, and here is an artist's depiction of it. You can see the disk around the protostar in the center. There is accretion coming from the disk, and the protostar is growing, contracting, and heating up. Often during this stage, there will be outflows of winds from the star and a pair of oppositely directed jets that are going above and below the disk here. Of real importance later on in this lecture is that this protostar is putting out a lot of ultraviolet radiation. This heats and effectively evaporates the gas in the disk. The system will eventually be swept clear of all the low-density material in the disk. As this protostar develops, as it produces more and more of this ultraviolet radiation, more and more of the low-density material in this disk will become evaporated, and you will leave only a debris disk. All of the gaseous stuff will be gone, and only the stuff that has collapsed to become high-density material will be left behind. Eventually, the protostar becomes a star. The core reaches an extremely high density and temperatures at millions of degrees, and this is when hydrogen fusion starts. That is when a star is born. A star turns on when hydrogen fusion starts in its core. This T-Tauri phase lasts for tens of millions of years. Now, let's move on to the formation of the planets. The first question when you're going to form planets in this disk is, what are the ingredients? What was the composition of the protostellar nebula? We used to think that we could look at comets as frozen remnants of the original protostellar nebula. The idea was that the comets formed in the outer parts of this protostellar nebula. They've been out there in this deep freeze for billions of years. If we just chop one open, we could see what the protostellar nebula was composed of. Unfortunately, as we've gotten to know comets, we see that their outsides have been processed heavily. They are covered with this carbon-rich gook. They're black as coal. They aren't really the original snowballs we thought they were. And their insides are rather puzzling in that they have materials coming that we believe form in the outer part of the solar system and in the inner part of the solar system. They do, however, provide some clues. We also find some clues among the meteorites. And among those, the carbonaceous chondrites are the least altered meteorites that we can find. And they provide a few more ideas. The rough ingredient list that we've divined from these sources is that you start with some dust grains. These are about 0.1 micron in size. And a micron is a millionth of a meter. Okay? This is the scale of thousands of atoms. You have these dust grains that are very, very small. They are composed basically of silicon, iron, and magnesium. Then you have gases, hydrogen, carbon dioxide, nitrogen, and ammonia. And in the outer parts, you'll have ices. And you'll find the ices in forms of snowflake-type objects and ice coatings on these small dust grains. The conditions in the disk when the planets form is that there is a temperature gradient. Remember, you've got this hot protostar in the center, so it's going to be hotter in the interior of the disk, and the farther you go out in the disk, the cooler it will get. This creates a volatility gradient. The ices, of course, can't exist right next to the protostar. They can only occur out in the outer regions. And the stuff that needs high temperature to form, that should only occur in the interior of this disk. You also have a density gradient. The disk material is flowing inward, which creates a logarithmic density profile, which basically just means that there's a lot more material per cubic meter at small radii than there is at large radii. And that means that the formation times should be shorter, because at higher density, you've already started at a higher density, so building up larger objects is going to be faster than if you start in the outer parts of the region of the disk. You actually have to build up the density to reach that high density before you can then start building up the objects. The last thing to consider about the disk is that there's a time factor, is that the low density material will be blown away in tens of millions of years. The rocky planet formation is dominated by accretion. This is the building up of large bodies from a myriad of small bodies. A rocky planet starts as millimeter-sized chondrules. This is an image of some chondrules in a chondritic meteorite. This is the cross-section of the meteorite, and all of these small circular things here, these are the chondrules. They are about a millimeter in size. They formed at very high temperatures, about 1500 degrees Kelvin, and they cooled very quickly. We can tell because of their characteristic shape. We're not really sure how these chondrules formed. You need something like lightning in the early disk in order to create these chondrules. But once you have them, the chondrules and the dust grains stick together via gravity and a little bit by electrostatic forces. When they build up and reach a few centimeters, then as they're orbiting, they start to have some gas drag on them. And that gas drag causes them to slowly spiral inward. As they're spiraling inward, that helps them sweep up more material. And eventually, they can reach sizes of 1 kilometer. And when you've reached the size of 1 kilometer, the gas drag through the protosolar nebula becomes negligible, and you have what we call a planetesimal. So it's the buildup from these chondrules all the way up to about 1 kilometer sized bodies at the beginning. Then the planetesimal collisions take over. The planetesimals, when they collide at slow velocity, will join together and stick together and become larger planetesimals. But if they come smashing together at high velocity, they'll actually break apart, and then they'll have all these small objects that can then, of course, get swept up by other planetesimals. This planetesimal accretion process is yet again a rich-get-richer scenario, and we quickly develop into a few hundred moon-sized bodies in the inner part of this protostellar disk. This only takes about 20,000 years. Then things slow down a bit. It takes millions of years for these to accrete together to form planets. Here is a computer simulation of planetesimal accretion. So, starts out with a few hundred moon-sized bodies in the top plot of this diagram, and as it moves down, the different plots in this diagram moving down the page show different times going through the simulation in the accretion of these bodies. Note that this takes, a few hundred million years in this simulation, but that the time doesn't really matter here because the low-density material that is swept away in tens of millions of years doesn't participate in these accretions. So this simulation ends up producing 4 planets, and it looks somewhat like our solar system. But it doesn't always have to produce 4 planets. You could run this simulation 100 times, and I don't know how many times you would get 4, but you certainly wouldn't get 4 every single time. As you go further out in the solar system, this takes care of the inner solar system. As you go further out in the solar system, the presence of Jupiter and its large mass is presumed to disrupt accretion out in the asteroid belt and even to affect the accretion of Mars a bit. Its large mass will scatter things all across the solar system, and it'll create resonances within the asteroid belt region that will disrupt its accretion. The total mass of all the asteroids in the asteroid belt, if you add it all together, is less than the mass of our moon. After you form these large bodies, you then get the heavy bombardment era, and this lasts for hundreds of millions of years. This cleans out the flotsam and jetsam in the solar system. There are a significant number of very big impacts, and we can see that evidence on the surface of Mars. Here, this very large impact structure is Hellas Basin, and there's another very large impact structure here, and you can see several other very large impacts on Mars. On Mercury, you see the giant Caloris Basin impact. On Venus, we see retrograde rotation, and we believe that somehow a giant impact was involved in slowing down and actually reversing Venus's rotation because all the other planets rotate in a prograde orbit. They rotate along with the same direction as they orbit around the Sun. And on Earth, well, we believe a Mars-sized impactor smashed into Earth to form the Moon. So all of the rocky planets show evidence of not just the heavy bombardment era, but very big impacts during the heavy bombardment era. Eventually, that bombardment calms down, the planets cool and solidify. Now we turn to the giant planet formation. And in this, a model called the core accretion model is favored. It starts with this planetesimal accretion to form a core. And basically it's the same process as form the rocky planets. These planetesimals accrete, and you pull in gas and ice from the nebula around that core. For the giant planets, note that more mass is available in the outer solar system because the area of an annulus, a disk around the Sun, the area of that annulus will be increased, and there will be more matter in that, more space to pull matter from, but that's also countered by the density decrease so that there is less mass per area available. Also note that ices are available to be incorporated into these planets because they form beyond the frost lines. First, there will be the water ice frost line at a temperature of 0 degrees, then ammonia at minus 80 degrees Celsius, and eventually methane at minus 180 degrees Celsius. So you establish first a rocky core of about 10 Earth masses, and this is enough to attract and hold the gas from the surrounding nebula. What happens is these giant planets become subcondensations in the nebula. They become their own little orbiting little systems, and stuff starts swirling and rotating around them. The rotation around them forms these subdisks, and within these subdisks, you accrete the regular moons and create the ring systems of these giant planets. Note that there are significant composition differences between the giant planets. Jupiter and Saturn are mostly hydrogen and helium, while Uranus and Neptune are mostly ices. The reasons for this are, well, probably twofold. First is the density gradient. As you go out from Jupiter, Saturn to Uranus and Neptune, there's not as much gas available. So perhaps Uranus and Neptune just couldn't pull in the gas because it just wasn't there. Also, we expect a slower formation timescale further out, so the nebula may have dissipated before Uranus and Neptune could attract gases. If Uranus and Neptune didn't form within the few tens of millions of years before the low-density material was blown away, the gas wouldn't be there for them to attract. The giant planets also experience a bombardment era, and if you look on the moons of these giant planets, the craters show abundant evidence of very large impacts. So the bombardment era was just as heavy in the outer solar system, and in fact, the giant planets are a major cause of the gravitational stirring that produces this bombardment era. This would also be the time when the giant planets capture their irregular moons, all those moons at the outer part that are on all these crazy orbits and not on a nice regular planar orbit around the planets. Finally, Uranus is rotating on its side. Somehow, we believe Uranus got tipped over on its side, and we attribute that to a giant impact during this heavy bombardment era. After that, well, the planets calm down. They cool and contract just like the protosun. However, they are still cooling and contracting today. This is a very extended period of this cooling and contraction. Jupiter, Saturn, and Neptune all give off more energy than they receive from the sun. For some reason, Uranus doesn't do this, and we really don't know why. Now, I want to note here something that you might read some places that's wrong. Some places you might see, oh, Jupiter is a failed star. This cooling and contraction didn't occur enough for fusion to ignite. It almost happened. Well, that isn't true. The simplest fusion, deuterium fusion, only occurs for objects about 15 times Jupiter's mass. So Jupiter never even came close to being a star. So that's the basic story of the formation of the solar system. But several very important questions still remain. Of importance is that the nebula dissipation sets the formation timescale. You only have a few tens of millions of years to form the planets. And we're not really sure if the rocky cores can build up fast enough so that you have the core for the giant planets to accrete all the gas and create the giant planet. There are also several alternate formation ideas for Uranus and Neptune. How do you get these guys? If it's hard enough to create a core for Jupiter, it's going to be even slower for Uranus and Neptune. And in this lecture, I've really only discussed the standard ideas. When you try and model the giant planet formation, the formation simulations show many possible outcomes. Here is a plot of several different simulations and their results. In panel A is our solar system as it exists. And if you look, and the other ones represent different runs of the simulation to see what they got. If you look at panel E, E looks, remarkably like our solar system. But if you look at F, F has 7 Neptune mass planets. Panel B here, well, that's got 1 Jupiter. That's about the same size as the Jupiter in our system. But if you look at panel G, it's got 3 Jupiters, and they're all several times larger than our Jupiter. This raises an intriguing point. Random chance seems to play an important role in how our solar system looks today. The last formation scenario we need to look at is for comets. Comets form in the outer solar system, basically from these snowflakes and ice-coated grains that I talked about earlier. The density is too low for them to form very large bodies. Now, as I talked about earlier, the composition of comets indicates mixing of the solar nebula, and that they are composed of stuff that must have formed in the inner regions and stuff that must have formed in the outer regions. This gravitational scattering by the giant planets seems to have been very efficient in scattering things all across the solar system. For the formation of the Kuiper belt, well, the idea is that the classical Kuiper belt forms in situ. This nice, organized, relatively circular feature of the outer solar system forms where it is, sort of like the way the asteroid belt forms. There would be approximately 100 million bodies of about a kilometer or larger that formed in the Kuiper belt. Then the evolution of the Kuiper belt is that Neptune creates the resonant Kuiper belt objects and also creates the scattered objects, both outward and inward, the objects that become centaurs. For the Oort cloud, the comets could not have formed where they are, way out at 50,000 AU. Rather, the idea is that the comets form near the giant planets and are gravitationally ejected to these very large radii. So they formed in the regions of the giant planets, and then the planets, especially Jupiter, shot them way out of the solar system, or even shot them out of the solar system altogether. There should be comets wandering through interstellar space. For the Oort cloud, the gravitational tugs of nearby stars further randomize their orbits. You got to recognize that 50,000 AU is about 20% of the distance to the nearest star. So the gravitational perturbations due to, for example, Alpha Centauri would be significant. It would be a few percent of the gravity due to our sun. This defines the gravitational boundary of our solar system. So that's the formation story for our solar system in detail. We can see that there are still a number of uncertainties, and there's really more randomness to this than a scientist would like, but the end result, at least for our solar system, turns out to be well ordered. If we refer back to this schematic, we can see that the collapse and rotation produce a nice circular disk and has a nice explanation for the gradient of materials. That we've got the rocky planets on the interior, the gas in the middle, and the icy stuff on the outside. This produces a stable system for the larger bodies. Now, you sometimes hear that the solar system is unstable, and that's not really true. Yes, there are perturbation timescales for the orbits of planets that are in the order of millions of years. But these perturbations become randomized, and it sort of becomes a random walk, and so the true instability timescale is actually billions of years. The main problem in looking at our solar system is that we only have one solar system to study. We do not know if the rest of the universe, if the other planetary systems out there behave similarly. And that is the next great change in our perspective, both in the solar system and in this course. Extrasolar planetary systems. We'll begin the exploration of those systems in our next lecture. See you then.